Thank you very much, Anastasia, for a nice introduction. And thank you for all being here today. So as you noticed from Anastasia's introduction, in the description of what I've been doing or I'm doing, there wasn't a single mention of AI. So a lot of you who know me for a long time might be wondering how come I'm standing here talking to you about AI today. And hopefully I'm going to introduce you to why we've developed a new AI tool using nested Monte Carlo Tree Search algorithm in order to design new specific small molecules for our desired target. And so, as I said, for those of you who know me, what I'm doing is, as most people in this division, looking at mechanism of regulation of drug resistance and metastasis in cancer. And in particular, we have our main research interest is in a family of kinases called the S6 kinases. And most of my lab is still working on such kinase with a subgroup working on the RSK subfamily of S6 kinase in the biology of lung and breast cancer, in particular, looking for new interactors, substrates, and molecular determinant of the function of these kinases. And I think we're the lab in the world that has been pushing further our knowledge of this kinase, and consistently we've published new findings about the role of RSK in cancer. Similarly, we've been very involved in highlighting the role of S6 kinase 2 in drug resistance and disease progression in cancer, in breast, lung, and now in osteosarcoma. And in particular, we found that HNRNPA1, an RNA binding protein, is a new substrate for S6 kinase 2, and another subgroup in my team is working on that. Outside of cancer, we've also looked at the role of S6 kinase in Parkinson's disease and cilia biology with co-supervised PhD students at other institutions. And apart from our research on S6 kinase, we're also involved in research on the crosstalk between cancer cells and cancer-associated fibroblasts, and a new project now on proteasomal inhibitor resistance in multiple myeloma. So as you can see, none of that screams AI research. So how did we end up being involved in developing this new AI tool? Well, it all started with one of the targets that I just told you about, which is HNRNPA1, which is phosphorylated downstream of S6 kinase 2. And at the time when we started on that journey, there was no inhibitor for S6 kinase 2. This since then changed, and through a collaboration with Germany, we have a kinase inhibitor for S6 kinase 2. And we had tried for many years to develop an inhibitor for S6 kinase 2, and we failed. So we thought maybe we should go one level down and try to develop an inhibitor for HNRNPA1. And the reason why we were interested in HNRNPA1 is because it's massively overexpressed in pretty much all cancer you can think of as compared to normal tissues. In fact, this is even more amazing since you know that HNRNPA1 is one of the most expressed protein in cells, if not the most expressed protein in cells. So despite that, cancers still find an advantage in overexpressing this protein. It mediates the drug resistance phenotype downstream of S6 kinase 2 signaling. So if you take out HNRNPA1, you lose the action of S6 kinase 2 in developing drug resistance. And we've demonstrated that in multiple cancer. And it does that by increasing the export of pro-survival mRNA out of the nucleus into the cytoplasm to maximize the translation. More recently, we also found that HNRNPA1 prevents cell death downstream of immune cytokines such as interferon gamma and TNF-alpha, which are involved in immune cells-induced cell death in cancer immunotherapy. And therefore, HNRNPA1 could prevent the immune clearance of tumors, and that could be a problem in terms of resistance to checkpoint inhibition. Finally, silencing HNRNPA1 appears to be more toxic to cancer cells than the normal counterpart, and therefore we thought we have there a therapeutic window that we could exploit. So HNRNPA1 seemed to be a great therapeutic target potentially, but it's an unconventional one because it's an RNA binding protein, so it's not kind of the target that most people go for. Regardless of this, in collaboration with Filippo Prischi, who came a few weeks back to give a talk here, we crystallized HNR-PA1 and then submitted the crystal structure to a fragment screen at the Oxford Particle Accelerator. So what you do is you've got a crystal for your protein, you add your chemical fragments binds or not, you get diffraction, X-ray diffraction, and you get a crystal structure of your protein in conjunction with the fragment that you add. So that enables you to discover chemical fragments that binds to the interesting pockets on your protein. And quite nicely, this was a great success technically. We found 38 fragments that bound onto regions of HNR and PA1 that are involved in RNA binding. So that told us that maybe if we took these fragments and expanded them into full-fledged molecules, we would be able to interfere with RNA binding. We then entered in collaboration with Apollo Therapeutics, and we got 132 molecules that integrated some of these fragments into larger molecules and then performed the screen on these molecules. And that's where disappointment came. What happens is that out of these 132 fragments, compounds, we found that they had affinity between 25 and 50 micromolar, which is essentially the affinity of the fragment themselves. So we had absolutely no improvement of affinity using these molecules. Not only that, but if we took the 5 top performing, if we can call these performing molecules, we found that none of them had any activity in cells whatsoever. So this was extremely depressing, and Filippo and I remained depressed for about a year and a half about it, until I attended an artificial intelligence conference in Paris. Don't ask me why I even wandered there, but I did. And at that conference, I bumped into Tristan Cazenave, who is the head of the PRAIRIE AI Institute in Paris, and his PhD student, then PhD student Milo, who are specialized in a type of AI algorithm called Monte Carlo Tree Search. So these are decision tree methodologies that basically lead to decision-making based on implementing policies. So in this particular case, yes or no policies. And he had applied this Monte Carlo Tree Search, MCTS, to multiple settings, including traffic prediction, water management, and games such as Go game and chess. And this is when I saw this image that Tristan had put in his presentation of Go game, looking at the black pawns surrounding white pawns. And so I don't know whether you guys know about Go, but the way you go about it is you're trying to strangle, opponent by stuffing his position with your own pawns. I thought, well, actually fitting the black pawns around the white pawns is pretty similar to what we're trying to do when we're trying to fit a molecule within the groove of a protein. So I approached Tristan and I said, well, do you think we could have a go at it? And bless him, he couldn't understand a word of what I was talking about, and I couldn't understand a word of what he was talking about because none of us had any experience in the other one's discipline at that point. But he says, yes, why not? And so we engaged in a project, and this was the idea in a nutshell. So MCTS decision trees are large language model. So it means that you use letters in order to progress within the trees. And so the idea was to do atom by atom compound generation. So you start with a carbon, and then you have the choice to add a carbon or something else. And then you have a choice to add a nitrogen to the carbon or an oxygen. And you go down the tree generating molecules. And you do that by processes that involve expansion. So for instance, you're at this position here, and you decide, why not select this possibility? And once you've selected this possibility, you operate what is called a playout, which is you just then ask the algorithm to randomly generate a molecule downstream of that starting point. The good thing is this algorithm can generate molecules which appear as a string format called SMILES. And the string format can be translated very efficiently into chemical structures. Then you take these chemical structures, and we can generate, let's say, 1,000 molecules at a time. and we apply them onto our crystal structure, get a predicted binding affinity for this 1,000 compound, and then this predicted binding affinity is given back to the algorithm, which through backpropagation, whether this was a success or not, decides to update these weights, which will then bias the decision-making for the next cycle and generate new molecules. So you carry on with this process over and over and over again until you cannot improve the affinity of the compound anymore. So you reach a plateau and you decide this is as good a molecule that I can get. You then, the idea is synthesize a few compounds. So the idea is 5 compound maximum, then go through in vitro testing, cellular testing, and in vivo testing. So the first problem that we had, and this is something that really surprised me, is that there is very little algorithm out there that can actually generate compounds that make sense. Most approaches that are publicly available, so I'm not talking of algorithms that are available in pharmaceutical company, produce non-valid molecules. What I mean by that is that if you ask them to generate 1,000 molecules and you go and you look at these compounds, the validity of these compounds may be as low as 4%. And this is because while it looks great on 2D on paper, when you're trying to generate these compounds in 3D, either they violate rules about binding of atoms, angles, and therefore they cannot exist in 3 dimensions, or they're so absolutely crazy that no one can synthesize them. So that's problem number 1. Problem number 2 is that most algorithms available out there use neural network. And these can be very computationally intensive and slowing down the process. So if we were to use, let's say, such an infrastructure before doing the docking and decision-making, the process would take either extremely long or would require very powerful computational presence. The third problem is that if you decide to go for a neural network, you will need a training data set. You will need to train that network for the decision-making that it's going to make. And then what do you choose as a data set? So if you choose, for instance, a collection of compounds that already exist, you're biasing the decision-making on the compounds that already exist. And for instance, the proportion of chemical space that we do currently explore in drug making is minuscule compared to the actual chemical space. So by doing that, we actually pass by novelty. In a way, the decision tree making, because of the random generation aspect, provide a solution to that last problem. So we started our project by testing various architecture for the Monte Carlo Tree Search. And the first thing that we considered was, first of all, do we need prior? And what we mean by prior is prior knowledge. Do we need to provide the algorithm prior knowledge in order to generate compounds? The first choice was no, we don't provide any, and we let the program generate molecule totally randomly. The second one is no, but we still enforce the probability of appearance of atoms, so carbon versus nitrogen versus chlorine versus oxygen, as present in the FDA. So at least like this, we are sure that we're going to generate molecules that don't have completely crazy atom proportion, like half of them are nitrogens, for instance. Then as an internal control, we used a neural network trained on the FDA. And the reason for that is because that's what we found to be the best performing out there until we came around. And therefore, we wanted to see whether we could perform better than that. And something else that we came up with was to use what is called n-gram. And what you're using here is the probability of 3 atoms occurring one after the other together with the bonds. So double bond, triple bonds, single bonds. And again, we looked at the FDA compound plus other drug molecules in clinical trial at the moment and learned from that the proportion the probability of these three atoms occurring together. And on top of that, we had some shortcuts. So things like the valence of sulfur, which can be 2, 4, or more. The type of cycles that are permitted, because when you go, for instance, for random generation or the algorithm that I told you about that only generate 4% valid molecules, you can end up with absolutely crazy cycle that you would never even imagine trying to synthesize. And we also implement a proportion of cycles. So how many 5-atom versus 6-atom cycles would you expect to see in a drug molecule? So this is for the prior knowledge that we provide or not to the system. Then, in order to generate valid drug-like molecule, we implemented a policy. So once the algorithm generates a compound, this compound is checked for whether or not it violates Lipinski rules. So Lipinski rules are still generally used in order to define whether a compound looks like a good drug. And so that puts limits on the molecular mass of the compound, the number of atoms, the number of hydrogen donor and acceptor, and some physical properties of stability, which is called log P. So that's for the basic architecture. But then basic Monte Carlo Tree Search suffers from a problem, which is called the multi-arm bandit problem. So that terms come from people playing slot machines. So slot machines were known as one-arm bandit. Why? Because they had one arm, and the bandit because they're stealing your money, right? So the problem of multi-arm bandit is the problem of someone sitting on a row of slot machine. He's sitting on his machine, and the problem is, do I stay on my machine that I've been playing on for 15 minutes because the next time I pull the lever is the time I may win? Or do I actually go on to the other machines that are along? Because maybe if I move to the next machine, then that's when I'm going to win at the next pull. And so that's a problem of exploitation, staying on your machine, or discovery, going onto other machines. And this is relevant to Monte Carlo Tree Search because, as I told you, the way that the weights in the decision tree are decided is through whether you had a success or not, and therefore learning from that success and saying, if this was successful, therefore I should use this path more. And if you repeat this 100 or 1,000 times, what may happen is this path is going to be super heavily exploited, but then that's going to be at the detriment of other paths that will never, ever be discovered. So we tested some variants. The first was basic MCTS as an internal control. And then we tested what is called nested Monte Carlo Tree Search, whereby at every single level of the decision tree, all possibilities are tested at the same time. So first level, you test all possibilities. You can see that this one produces better, so you select this one. And then all possibilities at this level, you select this one, and then all possibilities at this level. So that's maximum discovery. And then there is another architecture that we tested, which is called PUCT, which use hypervariables to balance discovery versus exploitation. So it's up to you to set these hypervariable to numbers that you consider would be interesting to test, and then you can see how the system behaves. So to cut a long story short, what we discovered is that in our case, a nested Monte Carlo Tree Search architecture with the n-gram prior and implementing Lipinski policy gave us the best result. And these are some results about the molecules that we generate. So we looked at generation time, validity of molecules, so whether they actually can exist in 3 dimensions, uniqueness, so is the same compound produced many times among 1,000 molecules that you generate, novelty, as in, are the compounds different from the FDA from which we generated the n-gram, proportion of proteins that have a log P inferior to 5, so that's in terms of solubility, and edit distance, which is within the 1,000 of molecules that you generate. What is the diversity among these molecules? Do they all look similar, or are they actually very different? And so what you can see is that in terms of generation time, PUCT was better, okay, at 0.5 seconds for 1,000 molecules generated, but not too distant from the nested Monte Carlo Tree Search at 0.7. But PUCT had the problem is that it hit internal maxima because of the shortcut. So we had to restart the algorithm continuously, which started making it random. So we decided against PUCT and then focused on the n-gram. But you can see that either n-gram, the n-gram nested Monte Carlo Tree Search or the PUCT were much faster than a neural network. Okay. So in terms of validity, the nested Monte Carlo Tree Search gave a 100% valid molecule, which is far higher than anything that was published so far. Most compounds are unique, so you don't get the same compound over and over when you generate 10,000 molecules. They are very novel in that although we learned from the FDA to generate the n-gram, 99.98% of the molecules generated are not equivalent to molecules that do exist in the FDA. They all have good solubility profile, and they are very dissimilar to one another. So anything above 10 shows low similarity between the compound generated. So all this was very good. And then we asked the next question, which is, now that we have the molecules, can we predict whether the molecules that we generate would be synthesizable? And for this, we used AI SynFinder, which is an algorithm that uses fragment library to retro-synthesize compounds. So if you say, this is my compound, can the algorithm find how to combine existing fragment to make that compound? And this is an algorithm that got trained on the FDA. And when we apply this algorithm to our molecules, the algorithm predicts that 32.2% of a molecule would be easily synthesizable. So that looks low until you discover that although the algorithm has been trained on the FDA, if you then take the FDA compounds and ask the algorithm, can you retrosynthesize them? Only 60% of the FDA compound can be retrosynthesized. So it tells you that actually 32.2% is not bad. And again, this figure is higher than the figure obtained for existing neural network. Apart from that, the structure of these compounds in terms of proportion of atoms, such as chlorine, fluorine, nitrogen, oxygen, sulfur, is similar between our n-gram approach and the proportion in the FDA compounds. And as you can see, much better in most cases than compounds that are randomly generated. And again, thanks to our shortcut, we keep the number of cycles within check, the physical property within check, and the aromaticity within check. We then did some more pharmacokinetics and ADMET prediction on these compounds. So we extended Lipinski rule to QED. So QED considers the variables of Lipinski rule plus some additional variables, such as the polar surface, the number of aromatic rings and rotatable bonds. And doing this, we find a high drug likeness prediction of 0.53. So that's good. Synthetic accessibility is another way you can assess whether or not your compounds can be synthesized. And any value between 1 and 5 means that the compounds are predicted to be easy to synthesize. And as you can see here, most of the compounds are below 5. And this is a proportion that is similar to the one in the FDA compound, but much better than if you just randomly generate compounds. The compounds are highly novel. So if you compare our compounds to the FDA compounds, most of them appear totally novel. And we determine this using the 10-nanometer index. We also check for pan-assay interference because it's not difficult to have a compound that binds to absolutely everything in the cell, like staurosporine being an example. And here what we can find is that only less than 5% of the compounds we generate are predicted to be what is called PAIN, so pan-assay interfering compounds. Finally, we looked at some metabolic assessments, and these compounds are mostly considered to be non-metabolically interfering, so none of the compounds interfered with 5-cytochrome P50, 4% only with 2 or more isoforms. Also, a very, very small proportion of these were predicted to be PGP substrates. And again, the deep PK analysis showed it to be comparable to the FDA with 80% of compounds predicted to be safe to the liver. Okay, so now we had an algorithm that could generate compounds. Now comes the second part of the question. Can we now use that algorithm to learn and develop compounds for targets? So I told you that we wanted to generate inhibitors for HNR-PA1, but that was a bit of a jump because we wouldn't have anything to compare it to see whether actually the algorithm is able to learn and deliver something of interest. So we took a step back and said, if we take proteins for which inhibitors do already exist, can our algorithm develop molecules that kind of look like the one you would expect to target these molecules, these proteins? And so we chose 2 proteins, the androgen receptor and HER2, for obvious reason for all of us who work in cancer. So these are our molecules that are involved respectively in prostate and breast cancer. But we made this choice also because the inhibitors for these targets are of different kind, because AR is a transcription factor, while HER2 is a tyrosine kinase receptor. And therefore, the inhibitors are either ligand competitors in the case of AR, or kinase inhibitors in the case of HER2. So we were able here to try to predict molecules that had different type of properties. And the advantage with taking such targets is there are many clinically used inhibitors for this target. So we could compare the molecules that we generate with existing compounds and seeing whether their property was similar. So the question was, can DrugSynthMC design compounds that would have superior or equivalent predicted binding affinity for these targets, or whether they engage residues within the target proteins that are similar to the clinical compounds. So in order to implement our algorithm, we therefore, as I said, decided to go for a nested Monte Carlo Tree Search strategy using 4 levels, and I'll tell you in a minute what that means. We generate 1,000 molecules per playout. So each time we go through a cycle, we generate 1,000 new molecules. We then dock these molecules on an average of the existing crystal structure for the target and alpha-fold structure. And the reason why we do that is that crystal structure do not have the same resolution depending on which part of the protein we look at. Sometimes also some part of disordered part of the proteins are not crystallized, and therefore we used AlphaFold to predict this and then average that structure. We then obtain an average docking energy using Autodock VINA, and we return this docking energy back to DrugSynthMC to improve the molecule in the next cycle. And what we needed to optimize in the learning process is how much weight do we give to the docking score versus Lipinski. So before we only had a single policy, which is, do the compound look like drug molecules according to Lipinski rule? But now we have an additional question, is how good is the binding affinity? So which one do you consider first? Drug likeness or binding affinity? And therefore, this introduced a question, do we need a single objective? So the single objective is the best binder possible, or a multi-objective where we mix the importance of binding versus drug likeness. So first of all, what do I mean by 4 level nested Monte Carlo Tree Search? And that's the multiple choice coverage that I told you about in nested Monte Carlo Tree Search. Instead of making it at one level only, we do it at 4 levels simultaneously. So we take 4 jump and then generate molecules. And this enables us to start implementing multi-policy decision. So in a single policy decision, the only thing that we considered was docking. So the only decision making was at the lower level here. We consider how good is the docking. So for instance, here 30, that's the one that is best. And therefore, the decision on the path to follow at 1 only depends on that docking. We then had a multi-policy implementation where we first look at how drug-like the molecule is. So here, 30, that's the best one. So this path is chosen. And then at this level, we consider how good is the docking. And then we make the decision on which path to follow based on the docking once we decide that the molecule is okay. And then we have the reverse policy where we decide, well, maybe the docking is the limiting factor because finding molecules that bind to your protein is the most important thing. And then once we find that, we decide whether or not they're good drug molecules. So that's the reverse multi-policy approach. So now are the results for AR and HER2. And you can see that with the multi-reverse policy, we end up finding molecules that have great pseudo-free energy. So here, the more minus the number is, the better the affinity of the predicted affinity of the compound for the protein. And so here for both targets, we've got pseudo-free energy that are pretty good. These are better than the multi approach. So the multi approach is where you look at whether the molecules are Lipinski-like first before you determine the docking affinity. And it's better simply because in this type of algorithm, as soon as the drug likeness is hit, the algorithm stops improving the compound. And actually, it is much easier to generate drug-like molecules than it is to develop good binder. And this is why here you can see that the binding affinity is awful. On the other hand, if we compare the multi-policy, where we compare first docking, then Lipinski rule, and the single policy where there is only binding, we can see that the binding affinity are similar between the two. But in the case of the single policy, the Lipinski scores are lower. So we still do improve the quality of the compound by using the multi-policy. So both binding and then Lipinski. So now how do the generated molecules compare to the clinical compound? So here you've got docking score. So again, the more minus it is, the best. Here Lipinski score, the higher it is, the best. And if you look at the reverse multi-policy, so here the green cloud for both HER2 and AR, what you can see is that the predicted affinity and Lipinski score for our generated molecules are either as good or better than the clinical compound, right? So now if we look at our generated compound and compare it to the clinical compound, are they kind of the same with some additions, some different groups, or are they very different? And here using the Tanimoto similarity coefficient, so 0.7 or higher means that they're very similar. Here we can see that for the compound generated for AR or HER2, we are below that number. So it means that our compounds are actually very different from the clinical compounds. Despite that, when we look at the residues on the protein that the clinical compound and our compound interact with, what we find is that a whole lot of these amino acids are the same. So here in the green box, you have the clinical compounds with the residues on the target protein they interact with. So here for AR, here for HER2. And here you have the best compound generated by our algorithm. And in red, you have the sites that are common in the docking between our compound and the clinical compound. And you can see that for some of them, a whole lot of the residues that our compound interact with are the same as the clinical compound. But can we do better? Can we even improve further this compound? The problem with nested Monte Carlo tree search is that it's very wasteful. Simply because here, for instance, we generate these compounds. So we end up with 10. We select that path. We generate some more compound. Now we've got 30 as a best success. And now these routes will be ignored. But the problem is, if you look at this path, for example, you can see that 20 is still an improvement over 10. So we had improvement here, but we're disregarding it. In fact, this improvement could be because of the addition of a grouping on the molecules that is very different from the group that was added to these molecules. The great thing with Monte Carlo Tree Search versus neural network is it's fully explainable. So you can go back and ask, what change have we introduced here that made this progress? And could we learn from this to improve further these compounds? And this is what we did. We looked, for instance, for one of our compounds that target the AR. You can see that it had a good affinity, a good Lipinski score. And we look at the compound and we took the scaffolds that make that compound out. And we asked, do other compounds that showed improvement had other substitution that we could learn from? And indeed, we found some groupings, chemical groups that could be added to the scaffold that were different between these molecules and other molecules that improved affinity. And if now we're taking these chemical groups and substitute our scaffold for these molecules, we can see that we keep the Lipinski-ness pretty much stable, but we dramatically improve the predicted affinity. So by doing this system, we kind of enable not to waste molecules in the decision tree and learn further to improve these compounds. And this increased affinity of these new compounds is due to the fact that as compared to the starting compound, with the new compounds, we now start increasing the number of residues on the protein that are common with the clinical compound. So we increase the number of known interactions that are linked with activity for this compound. Not only that, but we also start introducing some new interactions that are not seen in the clinical compound, and that may indeed improve further the activity of these molecules. So in conclusion, DrugSynthMC, I hope I could show you, is capable to learn compound to bind to specific targets. The target could be anything that has a three-dimensional molecule. So here I showed you protein, but you could very well imagine developing compounds that would interfere with mRNA, microRNA, anything you could determine a 3D structure for. So we use the AR and HER2 as a proof of concept, and it looks like compounds that are predicted here are potentially better even than the clinical available molecules. And so now we're looking at testing the 5 best compounds for each target into cellular assays to see indeed how they compare with existing clinical compounds. But something that I think I should make you aware of is that the whole process only took 2 weeks per target. So within 2 weeks, we develop molecules that look like they have a profile similar to molecules that are in the clinic now. So this versus the 1.5 years it took us to get 132 molecules that did absolutely nothing. So now we're trying to progress this towards a non-profit. So we're planning to start an organization which would sell the package algorithm, sell a drug discovery service based on this algorithm, and also host a web server for people to be able to connect and start doing the drug discovery on their own using this. But if you are interested in coming to us with a particular target and seeing how the algorithm would perform into developing a molecules for your target, just come to us and we'll be really happy to help you with this. Where are we going now in terms of trying to improve this further? So what I showed you at this moment is docking strategy made on a single conformation of the protein, which is the average of crystal structure plus AlphaFold prediction. The problem with these is that these are rigid structure, and a protein can actually move quite a bit and change conformation and go through transition stages. And some of these transition positions are actually better for the binding of some molecules than other. And so we're trying to implement that by using molecular dynamics instead of a single crystal structure, which gives us an ensemble of about 15 transitional states on which we're going to do the docking instead of doing it onto a single state. And hopefully this is going to improve the performance of the algorithm further. We're also trying BOLTS2, which is a new strategy that has been published now this year, which look at folding your compound within the protein. So it produces an auto-folding mechanism. And this has been shown to perform better than, for instance, Genina docking softwares. We're also trying to address a problem that we discovered as we developed this algorithm. And this is that what we expected would happen is that we would, with time, so increased number of cycles, see the affinity of the compound generated just smoothly progress until they plateau. And I told you, we reach convergence and we decide, okay, this is the best that we can have. In fact, what we observe is something more like this. And the reason for that is that, so here you're improving the affinity of the compound, and then the algorithm decides to go explore. And now the affinity goes down. And then it develops some compound with better affinity. And each time it goes explore new territory into the tree, the affinity goes down. So it is very difficult for us to implement a policy that says, when you reach that point, stop, because we never know where that point is. So we are trying at the moment 2 further variants of NMCTS, one called lazy NMCSC, which kind of prunes branch of the tree that seem to consistently perform less well. And by doing that, it will limit the exploration side of things, improve a bit on the exploitation, and hopefully make the curve a bit more like this. Another strategy that we are trying is called nested rollout policy adaptation, which is where the policy of deciding what is a good affinity evolves with time. So we can start low, and then as we hit the first compound, let's say that is at -5, we can say from now on, ignore anything that is not better than -5. And then adapt this policy as we go from one cycle to the next. And so these are two variants that we're currently trying. And so finally, who did the work? Well, that was a collaboration between 3 institutions, Imperial, with a master's student, Yali, King's College with Filippo Prischi, who was in charge of the structural biology docking side of things, and Tristan and Milo, where we developed the initial version of the algorithm, so the version that was producing just the molecules. And then the algorithm was further developed with Yali, but still in collaboration with Tristan. Tristan is the person who invented nested Monte Carlo Tree Search, so he was a great person to have on board for this. And that's it for me. I hope I didn't lose you on the way, and happy to answer any question.